The last type of problem we'll look at in this section are applications involving simple harmonic motion. So this this type of motion can be described either using a sine function or a cosine function. So we have a point moving along a coordinate line, and we say it's in simple harmonic motion if its distance from the origin at time t is given by either one of these functions. So the first one says distance is equal to a cosine of omega times t, and the second one says distance equals a sine of omega times t. And the a and omega are constants. Omega should be positive in the formula. So the a is the amplitude, of course. So this would be, let me draw a picture down here, give you an example. Like maybe you've got a spring, and that might even be, yeah, the spring is going to be in our next example. And you've got maybe a weight or something attached to it, and this is your equilibrium. So if you just hung the weight here and let it go where it would be at rest is the equilibrium. It doesn't just have to be up or down, it can also be left and right, but the point is that, this would be your 0, and then up is a positive motion and down is a negative motion. We use the signs to represent up or down motion, I should say. And if we're, think of your number line here, this is 0. If the max height is 5 and the minimum height below equilibrium is -5, the amplitude would be 5. So this weight, maybe you pull it down and let it go. So it goes down, up, etc. The motion being described by the cosine wave would have the object, well, let me start over. Let's do the sine wave. Remember, sine, when you graph it, starts in the middle, and then one period ends in the middle, and halfway in between is in the middle. So the sine wave would represent the motion if the spring is starting at the equilibrium point. And then if a is positive, it's going to be going up first and then down and then up and then down. If a is negative, it goes down first and then up. Okay? If it's a cosine wave, that tells you, so for t equals 0, cosine of 0 is 1. So this distance is a for t equals 0. The initial starting position then is up here. And now if that's negative, it's actually down here. So it also depends on the sign of a. But say it's positive, then we're up here. So first it'll go down and then up and down and up. So the function you use is determined by where the object starts. Okay? Now, of course, these are real simple models. We're only assuming a start of either at equilibrium or at the high point or the low point. Again, this could all be thought of as left and right motion also, right? So this would be a and this would be negative a, and it's just going back and forth, right and left, right and left. Now, in reality, if you took a spring and did that, it would eventually, because of friction, slow down and go back to rest. But we're assuming that it will keep this motion forever, back and forth, back and forth. Just making it simple. Okay, that's why it's simple harmonic motion. All right, so the amplitude, we talked about that. It's going to be the absolute value of a. That's the maximum distance the object will be from the origin. Of course, it can happen on either side of the origin. The period then, well, that's just our usual formula for the period. We're using omega instead of b. We could have used b as well, but 2 pi over omega. It's the same formula, nothing new there. Then the frequency is the number of cycles per unit of time. So if you take 1 over the period, that will give you the frequency. And we'll do an example here, and I'll explain the units when we do the example. Okay? So let's go ahead and do an example. So this example, we have a weight attached to a spring, like I talked about before, and the distance is given by the formula -5 sine pi over 4 times t. So before I actually answer these questions, let's what's happening with the motion here. So notice that t equals 0, that's our initial position. Let's see, this is our weight again, and here's our spring. Okay, so it's at 0. Well, it's not necessarily at 0, but I'm getting ahead of myself. At t equals 0, the sign of 0 is 0, so that is the initial position. So this is the distance in centimeters. So right now it's at 0 centimeters. Then what's going to happen is, excuse me, because this is negative, think about your sine wave, or your sine value as you go around the unit circle. It's positive first, so this is first going to become negative. And it's going to be at its minimum value for the first time when t is 2. And how do I know that? Well, I'm thinking ahead and saying, well, sine of pi over 2 is 1, so that means t would have to be 2. So at t equals 2, this thing is down at the minimum value. It's a point of maximum displacement. This would be at -5 centimeters. Whoa, I don't know why I wrote MC instead of CM. That was weird. I do that sometimes. So that's our D. So distance really isn't negative. This negative here is representing the fact that we're at the below equilibrium. And then sine is 0 again at pi. So when t is 4, so now here t is 4 again, we're back to equilibrium. And then it's going to start going up. Okay? And 3 pi over 2 is where sine is -1, so that's where we would, if we're at our max at 5 centimeters, it's going to be when this is 3 pi over 4, or 3 pi over 2, excuse me. So I could just solve that for t, and that's when t is 3 pi over 2 times 4 over pi, and so that would be 6 seconds. And notice these are all 2 seconds apart, so it shouldn't be a surprise. Same amount of time takes to get from, each point here. And then it'll be another 2 seconds and you're back at equilibrium. So this keeps hitting equilibrium every, 4 seconds. Okay? So down, up, up, and then down, and you've completed one cycle. Alright, so let's answer the questions, and we kind of already know the answers now. Find the maximum displacement from rest. That would be 5. That's just the absolute value of -5. And then label that, it's centimeters. B, time required for one cycle. We already talked about it. Down, then all the way up, and then down is 8 seconds, right? But no, that is the period. The period tells you the length of time it takes for the motion to complete one full cycle, right? That's the definition there. So for B, it'd be 2 pi, we already know it's 8, but I'm going to use the formula. 2 pi over omega is pi over 4. So 2 pi times 4 over pi is 8 seconds. And then C, the frequency, and the frequency is the number of cycles per unit of time. So this is 8 seconds. The period is 8 seconds for one cycle. Whoops. Can't spell. For one cycle. So the frequency is the reciprocal of that. So yes, the reciprocal of this, but if you have the 8, you actually already have the answer, right? This is 1 over 8. I would just use this, reciprocal of that. And then it would be 1/8 of a cycle per second. Now the units of time could be different, of course, but this is seconds because that's what we're given in the problem. 1/8 cycles per second. So frequency is how many cycles per unit of time. You're only, for 1 second, Right? It takes 2 seconds just to get down to here. So you only get, in 1 second, only an eighth of the way, an eighth of the trip. Okay? So find the period first, and then the frequency is simply the reciprocal. And units will be the reciprocal. This is, period is 8 seconds. Well, we don't usually tack this on, but interpretation is 8 seconds for 1 cycle. So then the frequency would be cycles per second, or whatever the unit of time is. Okay, well, let me know if you have any questions about that.